each day we have a parallel session.
Give me.
And the distribution of parallel session is based on west to on this side, on the same floor. On the other side there is south. Next to this there is a cinema. So on the first floor we have 5 halls for parallel session. At the ground. Yeah. First floor we have parallel rooms. So west 1, west 2, we are here, and another we have a cinema. On the other side of the dining area, we have south 1 and south 2. No problem. So in the first floor we have 5 parallel sessions. This is just to draw your attention that the parallel sessions will be conducted in 8 such conference rooms. And that will be a part of our daily schedule in the afternoon. So we are at West 2, and each session will be chaired and it will be co-chaired, and they'll be honored with conducting the session. Each session will be starting with a thematic presentation, followed by the presentation by the authors of the paper. So with this brief word of introduction, on behalf of the committee, I hand over the session to the chairs and the co-chair so that they are able to complete the session well within the time. Thank you very much.
Thank you, sir. So, good afternoon. This the first parallel session of this conference. We'll welcome you all. Me, Vivi Maji, and Bapati Tamanna, Professor Bapati Tamanna, both I'm chairing this session. And our session title is The Rock Mechanics and Tunneling Engineering. So the first, as sir already mentioned, we have one thematic lecture followed by some of the contributing paper presentation. So the first, the thematic lecture is being given by Professor Preeti Maheshwari from IIT Roorkee. So she doesn't need any introduction, but just briefly I'll tell about her. I think she has done her PhD in from IIT Kanpur, mostly in geosynthetic field, and then she is a faculty in IIT Roorkee and working in also in tunneling and rock mechanics field and other geotechnical areas. So, so with this brief introduction of Preeti Maheshwari, I just request her to give a lecture. So yeah, you have 15 minutes.
Yes. A very good afternoon to all of you. Do I need to use mic?
Better, I think, because that's the
Okay. Okay. So, a very good afternoon to all of you. I am Preeti Maheshwari from IIT Roorkee. So, I'm going to discuss with you about this work that we are doing as a part of one of our sponsored research project from DST, and I am going to discuss a particular aspect of this work, which is related to probabilistic analysis of a wellbore in rocks. So this is going to be the overview. Like first I'll try introduce the problem, followed by how we did the analysis, few results, and the concluding remarks. So before we start taking up any probabilistic analysis, first we need to understand that what all can be the causes of the uncertainty in that particular material. And as geotechnical engineer, we deal with these two materials which have lot of uncertainty. Both are natural occurring material, that is soil and rock. So here is a picture which shows the rock mass which exists in the field, and you can see that as the size of the circle increases, you see that more number of joints they come into picture. So if we take a very small circle and if we try to take out the sample from that, we call it as intact rock, which is not having any kind of discontinuity. However, if you just take a zoom version of this intact rock, you see that there are several micro cracks which are present. Now these micro cracks and their distribution, it can be totally random. The number of micro cracks also can be really different from the same sample. If we extract multiple specimens, these can be altogether different. So what they do is, when the mechanical characterization, which is done usually on the intact rock in the lab, when that is done, let us say you conduct say 50 tests, you will never get a single value of say UCS or the triaxial characteristic. Okay, so this causes our material to become uncertain or the random, which really cannot be handled by our conventional way of analysis, which is deterministic. So there are different types of uncertainties which are there. So two which we can handle with the help of testing more number of specimens and with the help of testing the specimens of a particular size. Say for example, NX size, which is 54 mm in diameter with L by D ratio as 2, of course the cylindrical specimen. So these two types of uncertainties can be handled. And when we talk about the mechanical characterization of the rocks, these are the typical tests that we go for. Now, please see that this is the test, these are the test results that we did on a particular type of rock, which was sandstone from a particular area, and we conducted more than 100 tests and see the variation. It's the one test only under the same condition on different specimens, and you can see how the variability is there. The question comes, if we are handling the statistical and the other type of uncertainty, then why are we getting this type of variation when we test more than one specimen? So that accounts for the inherent variability, for which if we want to handle these properly, one has to consider the uncertainty of the material in the form of the probabilistic analysis. So with this background that why such analysis are needed, I would go ahead, because then we discussed, or in this part of the presentation, I am going to take up a problem which is related to the stability of the wellbore. You all must be aware that why these wellbores are needed. When you have the oil or gas extraction, then one has to go for the wellbore, and the stability of these wellbore becomes really very important, because how much should be the mud pressure so that the walls of the wellbore, they are stable, they do not collapse. All these things depend on how we design these wellbores. So this is a typical figure which is giving you the idea that how this whole system looks like. Now if we take a cross section at any particular depth, and if we see the plan of that, it will look like this. Okay, so this is a wellbore with the radius say Ri. Okay, this Pi is representing the pressure that is being created by the mud that has been filled there, and this is the in situ state of stress. And of course, when this situation is there, in the vicinity of the wellbore, you will have some kind of broken rock, and beyond that, you will have the intact rock which is elastic, and in between we will have this elastoplastic boundary. So this is actually a classical problem of this elastoplastic analysis of a circular underground excavation. So this is typical, the geometry and the loading condition. So what we did for conduct of the probabilistic analysis, we have chosen the technique called Monte Carlo simulation. And we all are aware that for any Monte Carlo simulations, we need a deterministic model. So first I will just discuss the deterministic model. Then I will show you that how we conducted the Monte Carlo simulations and how we analyzed those results. So here the assumptions which were involved in the deterministic analysis, that we considered it an axisymmetric problem. We considered the elastic, perfectly plastic behavior of the rock mass, and we represented that rock mass as the with the help of the Moore Coulomb failure criterion. And this assumption that we made, thinking that okay, the size of the well bore is very small as compared to the discontinuity, geological discontinuities which may be there. So maybe we can consider the rock mass as the intact rock material. Why we did that is that in the lab, whatever that we have tested, the material parameter that we have obtained, the criterion parameter, that was done on the basis of the testing on the intact rock, not the rock mass. So we are just trying to directly use those lab test results for this analysis. So we made this assumption. Now I will not go into the mathematics. Some of the important parameters that we would like to study is the radius of the elastoplastic boundary, the stresses and the radial displacement that would be happening, because they will be controlling factor for the design of this well bore stability and the subsequent drilling operations. So I'm not going into the mathematics that how we derive. We took from the basic principles of mechanics, we derived these. So I will just skip these, some of these expressions. So there we have derived the stresses and the radial displacement in the elastic domain and also in the elastoplastic domain, where it was the broken rock in the vicinity of the well bore. So coming directly to the probabilistic analysis, so these are the results that we obtained from our analysis of the test data. That first we did the deterministic analysis, and then because we had the multiple tests under similar condition, so we have fitted the distribution, like which one is the best distribution representing the data. And then we found out that how many number of simulations are required for a particular error and the confidence level. Accordingly, we performed 2,300 simulations. And please see here the results. So this is for the tangential stresses all along the in the radial direction, like R by Ri equal to 1 means you are at the well bore periphery, and then we are going in that direction. And the second one is the result for the radial displacement. Kindly note that the variation after 2,300 simulation with those parameters that we got from the lab, see the variation. Instead of a unique value, here we are getting 2,300 plots for radial as well as the tangential stresses. Now please see this. Just give me a minute. It is asking for the restart. Okay, so I will say not now. Yeah. So now see here, this is really very interesting. This is what that we have plotted the radial displacement, and I have normalized it with the radius of the well bore. And what we realize that the variation in the displacement, or I should say the randomness in the displacement, was much more as compared to the stresses, radial as well as the tangential stresses here. So after getting this, we took, let us say here, the maximum value of the radial displacement and the maximum stresses wherever they were occurring, and then we carried out the analysis. But before I go to that analysis, the extent of the elastoplastic region or the location of the elastoplastic boundary is very, very important a parameter. because accordingly then you provide the support system, or here in this case the mud pressure, okay, accordingly that we have to do. So here what we did, whatever are the simulation results were there, we tried to see, okay, which distribution is representing better this particular variable. So here you can see that we tried with gamma, normal, log normal and Weibull distribution. Why we chose these 4 distributions? Because most of our geological discontinuities or the geological processes, they are very much well defined by some of these distributions. So we took these 4, and you can see that except for the Weibull distribution, here all these 3 distribution, they are like more or less close to each other. So but then of course we conducted these statistical tests such as chi-square test and KS test, and we have done all those analysis, not going into the details of those mathematics. So then we did whatever were the results of the Monte Carlo simulation with reference to the radius of the elastoplastic boundary. Here we tried plotted them. What is the need for this? Because when we are doing it, let us say if I have a particular value of the radius of the elastoplastic boundary, after doing this probabilistic analysis, I should be in a position to quantify the risk associated with that, or I should be able to find out that what is the probability that a particular radius value will occur or it will be less than that. So for example, here I have shown that, okay, there is going to be about 26% of the probability for this particular case which we have taken, that the radius of the elastoplastic boundary will be less than or equal to 0.16 meter. Similarly, we carried out this analysis with respect to the tangential stresses. So we have taken the stresses, critical stress, tangential stress value at 2 locations, one at the tunnel boundary, which is represented by sigma theta I, and one at the elastoplastic boundary. So please note here that at the tunnel boundary, it is about 42% probability that the stress will be less than or equal to 120 MPa, and similarly here also we can quantify. So nothing very specific about these 2 values, that is 120 or 184 or 34 or 42. This is just that I am just trying to show you that, okay, this is how we can use these results in order to quantify the risk associated with any value of the tangential stress. So similarly here, if we talk about the strain, see, I don't know how many of you are involved in the design of the wellbore, but this is very much related to the permissible strain level, okay. So for a permissible strain, you need to find out that what is going to be this risk which is associated with that, and according to that you will choose the mud pressure inside the wellbore. So like that, here we have done the analysis. Again, I took a particular value, let us say 33% of the 0.33% of the strain here, and corresponding to that is the 36% of the probability of failure, which is, or the probability is there that the strain levels are going to be less than or equal to 0.33 percentage. So this is a small analysis, and we just tried to give the idea that how we can connect the test that we are doing it in the field and towards the probabilistic analysis, okay. So some of the key points which I would like to highlight here, that the uncertainty which is associated with the design parameters, yes, we are able to quantify this using the probabilistic analysis, which we cannot do by the conventional deterministic analysis. Then here, of course, as I mentioned, that for a permissible strain level, we need to know the risk which is associated, which we are able to do here, and then some of these values which I have already discussed. So basically, this information is going to be helpful for us in deciding the critical mud pressure and then subsequent safe drilling and the other operations during the oil or the gas extraction from the wellbore. So I would like to acknowledge the funding from SCRB. This is a part of our sponsored research project. So thank you very much. Okay.
So,
Okay.
I have one just clarification.
Yes.
You mentioned some permissible strain. So it is borehole applications. Is there any guidelines on that?
Yes, there are. There are. So it depends upon what is the state of stress, in situ state of stress, and few other parameters there are.
Thank you, Professor Preeti. I think it was
Thank you.
interesting talk and work. So thank you so much.
Thank you.
So we'll continue with the contributing paper presentation. So first, my colleague Professor Bapaditya Manna will continue with calling the names.
Yeah. So the first contributed presentation, the title is Preserving Heritage, Geologic and Geotechnical Strategies for Restoring and Historic Tunnels. Who is the speaker? What's your name?
Francis Bernal.
Francis. Okay. So you have 9 minutes time.
9 minutes.
9 minutes.
Okay, so good afternoon. I'm Francis Bernales from AMH Philippines. So for this presentation, we're going to talk about preserving heritage and all the geologic and geotechnical strategies for restoring a historic tunnel in the spirit of heritage preservation. So let's focus for the moment in the pictures shown in the slide. So some of you may think that definitely it's an old tunnel. Some of you are thinking maybe a creepy cave or a dungeon. And some of you may also think that's already deteriorating. So regardless, I think we can all agree that this tunnel is a marvel of the past, created by old engineers, old construction workers, using simplified methods of tunnel excavation. So tunneling practices have also evolved immensely with centuries of practice. So as we will find out later on, some of you will discuss all the modern tunneling technologies. And some of these, however, some of these old structures, tunnel structures, something like this, have stood the test of time. And preserving these types of historic tunnel structures are challenging, mainly because some of the old engineers doing the work haven't done the paperwork to document all the details of the tunnel construction. So for this case study, we're going to talk about an old tunnel that's located in the Philippines, right in the heart of metropolitan Manila. So this one is actually built below the on a minor seminary called Our Lady of Guadalupe Minor Seminary. So it's a Roman Catholic seminary. So at the time it was built in around 1955, I didn't know that there's an old tunnel below them. So eventually they discovered that it's an old tunnel according to local accounts. It's an old tunnel built by the Japanese during World War II. So we're going to talk about that, all the strategies that we've developed in order to restore the tunnel. So for this presentation, we'll talk about the site characterization tools that we did, the geomechanical analysis to evaluate and assess the old tunnel, and discuss all the results and discussion, mainly on the recommendations for implementation, and wrap it up with some concluding remarks. So for the site characterization, first, we deployed a team or solicited a group of drillers, to do the rock core drilling right at the tunnel walls. And we want to have rock samples that we can test for unconfined compression tests so that we can get an unconfined compression strength. And then we also did some Schmid rebound hammer testing. That is to assess the rock hardness in order to we can relate it to the rock strength. And also we deployed a team of surveyors for ground penetrating radar. And that is mainly to, at that time, to trace or like locate the alignment of the tunnel below it. So shown in red is estimated or like the predicted tunnel trace after the GPR survey. So as you can see here, this is the this is the plan of the entire seminary. So based on the GPR survey results, we estimated that this is the location of the tunnel trace. And then also shown in the map are the locations that where rock cores were extracted, and also the remount hammer test. So a typical section shown here is where we did the rock coring as well as the rebound hammer testing. So further, our group of geologists conducted a field geologic survey in order to map all the geologic structures found inside the tunnel. So as you can see here, this is a typical field geologic map of all the structures here. And also, they tried to evaluate each of these parameters. Mainly, for the rock mass characterization, we will focus on the Q system. So some of you may not be familiar with the Q system. It's basically a rock mass characterization system where you want to classify the degree of jointing, the joint friction, and as well as the active stress, taking into account the effect of joint water, as well as the internal or overburden stresses in the tunnel, inside the tunnel. So, moreover, we also deployed a team who conducted a geometric survey using terrestrial LiDAR. So a sample product is this. So similar to the map that I shown previously, this is the 3D rendered with the actual texture, and in the plan view we can clearly see the location of the LiDARs of the tunnel structure below the buildings in the seminary. And also we used this tunnel geometry, 3D tunnel geometry, in order to extract cross sections, which we evaluated for and which we used to have a cross section drawings of per station inside the tunnel. So proceeding with the geomechanical analysis, we mainly did two things. First is the finite element analysis of a typical cross section of the tunnel. So as you can see here, this is a typical tunnel, and we want to idealize it for our FEM model. So we included the shotcrete lining, the rock bolts, as well as the building built on top of it. And we use mainly the site characteristics as shown previously, the rock properties that were characterized using our rock mass characterization system, and based on the known support properties that will be proposed later on. So unfortunately, we don't have time to discuss the details of the numerical modeling, but you can refer to the paper for more details. But for this, we want to just to emphasize that the FEM is very valuable in order to have a simultaneous evaluation of both the displacement and the stresses in order to evaluate the stability of the existing tunnel. So we were not satisfied with the FEM model because it just models the rock mass as a continuum. So we also want to look at how the jointing, what if the jointing controls the tunnel behavior. So we did some discontinuum analysis. So first, we did a kinematic and jointing analysis of all the geologic structures that were mapped for the tunnel. So we want to do that to assess the potential for rock mass failures, and this is mainly based on the orientation of the discontinuities, the joints, the bedding planes, the faults, relative to the tunnel face. So we use DIPS to evaluate this, and it shows low percentage of wedge failures. As you can see here, there's small clusters of intersecting wedges. However, the major trends are dominantly perpendicular to the tunnel axis, and it's against the tunnel drive, so that's actually favorable for the stability. So furthermore, we want to evaluate the wedge stability that was revealed in the kinematic analysis. So we use unwedge to automate the calculation of all the possible combinations of wedge failures. So we found out that the local wedges are fairly stable, factor of safety greater than 3, and that the tunnel can maintain stability with no additional support given the current conditions. So spot bolting is essential for areas, however, with fractured or loose ground. So moving on to the results and discussion mainly on the recommendations for construction implementation. So we first use this rock mass quality and rock support chart given in the Q system to have an initial support support configuration. So mainly this is a factor of a span or the geometry of the tunnel divided by the excavation support ratio. So mainly this is the ESR is mainly determined by the safety requirements and a function of the occupancy category of a certain tunnel. So the higher the ESR, you're mainly talking about temporary mine openings, and the lower the ESR, you're talking about critical tunnels. So for this one, we use it in order to have, in addition to the rock quality range or the Q value range, we determined that the reinforcement types will mainly lie under category 1, which is mainly spot bolting for local wedges. So with that, if ever for local spot bolting, we recommended to use glass fiber reinforced polymer or GFRP rock bolts, and this is best for this purpose because this is a fairly short or fairly small tunnel, about 4 to 5 meters at most. So you don't want to deploy large equipment using mainly using steel bolts. So we want to have lightweight, this easy to install inside the tunnel. So in addition to that, whenever possible, we want to have fiber reinforced shotcrete in order to have a tunnel lining in order to protect it against water ingress. And for the portals, we want to have steel ribs in order to reinforce the stability of the port, to address the instability of the portals as well. So an additional construction consideration is a seepage and seepage control and drainage. So you want to have some waterproofing as well, and furthermore, you want to have a field monitoring, consistent field monitoring and documentation of the future behavior of the tunnel as well. And lastly, we also want to have aesthetic considerations. That's why we have to implement tunnel portals and also tunnel lining in order to have some architectural inputs as well. So in conclusion, so this study, hopefully you were able to see how modern engineering tools were integrated in order to address the complexities of historic infrastructure. And we used geophysical, geodetic, field investigation, and lab testing in order to create a geologic and geometric model for the tunnel structure. So it's also important to balance the continuum or the finite element analysis, which is fairly popular in the engineering world, as well as the discontinuum analysis using wedge or kinematic analysis for checking the stability under the existing loads. And for the FEA, it revealed that displacement levels are well within the tolerable limits. And for the discontinuum analysis, the wedge failure is fairly minimal. So any local instability can be easily mitigated with targeted support, such as spot bolting or fiber reinforced shotcreting whenever it's needed. And ultimately, the design strategies implemented here prioritize both safety and constructability while maintaining the tunnel's historic value. So just to wrap it up, a recurring theme in this conference is mainly that we always should balance tradition with innovation, and I think this study is consistent with that idea. So just to acknowledge our co-authors for this paper, as well as all the our co-workers for this project that contributed a lot in this work. So just a few seconds to flash the references, and I would like to thank also the organizing committee of the Geotech Asia for this conference as well. Thank you.
Thank you, Francis.
One small clarification. You have shown for unwedge analysis factor of safety greater than 3.
Yes.
So any specific codal requirement was there? Why you have taken 3?
No, there's no specific. I don't think there's a specific guideline for this, but I think that's a judgment call in that part. That the factor of safety of 3 is fairly conservative for this type of project. But the short answer is there's no specific guideline for that. Just a judgment call.
Okay, thank you.
Okay, thank you very much. So the next presentation is back analysis of volume loss from tunneling in Chennai formations. Your good name, please? Parimala. So 9 minutes.
Good afternoon and all. Today I'm going to discuss about back analysis of volume loss from tunneling in Chennai formation. Myself Parimala, I'm from ACOM. Is it working? Yeah. Yeah. So I think there is problem with the formatting. Yeah. Okay. As here, as the tunnel is being built, the ground settlement mainly happens due to volume loss. So, however, we don't have there is limited published data for the volume loss, which is happening in the formations like in Chennai. So, what we have done is we have taken the Chennai Metro Phase 2 project details. So, where the ground settlement markers are installed. So, the project is currently ongoing. So, we have utilized that data for back calculating the volume loss. We have also utilized the Plaxis 2D software for back analysis, and we try to determine what is the volume loss. And also, we fitted the Gaussian curve to determine the trough width parameters for the Chennai formations. So, yes, TBM tunnel, sir. So this is the route map of Corridor 4 underground stretch. So Corridor 4 runs for 10.3 kilometers underground stretch. So currently the tunneling is going on from Lighthouse to Kacheri, and then Panagal Park to Kodambakam. So the details have been used currently. So Lighthouse to Kacheri, we have tunneling phase, we have silty sand, which is underwater, and overburden, we have silty sand and clay. From Panagal Park to Kodambakam stretch, tunneling phase, we have silty clay, which is also underwater, and overburden, we have silty clay in some areas, and some areas we have mix of silty clay and sand. So conventional prediction of settlements due to boat tunnel. So the settlement curve induced by a circular tunnel excavation is assumed as Gaussian shaped, with maximum settlement as S max, and volume loss is VL, and D is the diameter of the tunnel. Sorry. Okay, D is the diameter of the tunnel. I is the horizontal distance to the point of inflection. So for the higher overburden, for example, if we have overburden higher than the tunnel diameter, we can utilize the formula of I of K times Z0. K is the trough width parameter, Z0 is the depth of the to the tunnel axis. So for determining settlements using empirical method, we require volume loss and trough width parameter. So volume loss definition is like volume loss is like is the difference between volume of the ground that should ideally be displaced and the actual volume of the ground that is actually be displaced. So volume loss mainly happening in the tunnels is due to phase loss, shield loss, and tail loss, and other long-term losses. So it is normally expressed in percentage, that is volume of ground loss to the volume of tunnel excavated. So trough width parameter, it controls the shape of the Gaussian settlement curve. So higher the K, broader and shallower the settlement trough, and lower the K, narrower and deeper the settlement trough. So it depends on geological strata. So various authors have suggested different K values for example, O'Reilly and New have suggested 0.5, Chiriotti et al. Have given cohesionless soil 0.3 and cohesive soils 0.5. Berland, granular soil 0.2 to 0.3, stiff clays 0.4 to 0.5, soft clays up to 0.7, and Ku has given average of 0.6. So this is a typical instrumentation monitoring array that has been used for this Chennai Metro project, which has ground settlement markers around 7 to 9 numbers, and standpipe piezometer, rod extensometer, tunnel convergence. So these are all spaced at every 25 to 50 meters. So the data from the ground settlement markers have been utilized for this study. So although we have for every 25 to 50 meters data, we have taken a data where the data is reliable and there is not much influence from the buildings, and at least we have ground cover of 1.5 times the diameter. So from Lighthouse to Kacheri, we have utilized the array information of D14 and D22. Panagalpattu to Kodambakam, we have utilized T6 to D15. So this is just a typical ground settlement we have got from the instrument data. For array D22 from Lighthouse to Kacheri. So if you see for a particular, this is the first arrival of first TBM is marked here, and arrival of second TBM. So before the arrival of TBM, there is a ground settlements happening at that particular point is due to the phase loss ahead of the tunnel. So we have used the Plaxis 2D for modeling the settlements, so tunnels and settlements. Here volume loss is modeled as using line contraction option. So first we have given the assumed volume loss, and then we have arrived the settlements from the Plaxis. Then we have plotted and we have compared with the settlements, observed settlements, and we have back calculated the volume loss. This is the typical plot. So volume loss for Panagalpattu to Kodambakam, we have got around, when the first tunnel passed 0.12 and second tunnel 0.14. And for D15 array, we got around 0.15 to 0.11. Lighthouse, we have got around 0.7, 0.5, and Lighthouse to another array, 1.5 and 0.5. Similarly, we have done the K parameter determination by using the empirical formula I have shown. In that formula, we have back calculated the K parameter. So K parameter of 0.5 to 0.4 is obtained for clay sand mixture, and for sand we have got around 0.35 to 0.5 range. So Charnakite is the bedrock which is found in Chennai region, which is granitic formation. So we have not obtained that kind of stretch. We are not in this corridor 4. So we have taken the data from the corridor 3 and did the similar assessment to determine the volume loss and K parameter for the Charnakite rock as well. So volume loss of 0.4 to 0.5 is obtained for Charnakite, and K parameter of 0.8 was obtained for Charnakite rock. So conclusion, back analysis showed that volume loss of 0.11 to 1.5, and trough width parameter was obviously dependent on geological strata. For silty sand and poorly graded sand, we have got around 0.35 to 0.4, and mixed clays and fixes, we got around 0.4 to 0.5. Charnakite rocks, we have got around 0.8. So these findings will be useful for upcoming stretches. Yeah.
Question, please.
Very nice presentation,
Thank you, sir.
Parimal. So you mentioned about Charnokite rock. What is that volume loss in reference to Charnokite? It is like you have the top layer soil, right?
Yes, sir. Face, we have fully in rock, and
but the cover to some
soil cover is
body there.
yeah.
So then
soil is
how,
there.
what exactly, like how you interpret the volume loss in that scenario? Like any suggestion on that?
So volume loss we have back.
Charnokite rock.
Okay. Not entirely in that rock, sir. Anyway, that mixture is only we have got. Yeah. Yes, sir.
Okay, soil rock together.
Yes. It's not.
You have a soil and you have soil rock together. That also I think
Yes, sir. Thank you.
Thank you very much. So I think third presenter is not available. Still I'm taking the title. That is 10 response of the existing tunnel to instability of the new tunnel support. Is the author present here? Okay, no. So then we can move to the fourth presentation. That is, 3D analysis of Tibian tunneling effect in layered soil using Midas GTS NX.
Good afternoon, everyone. So this is the work done by our team members. So I'd like to first appreciate all of them here. Jyoti is the key person involved who did the analysis, and we all were there to support her as and when required. So I'm presenting on the behalf of our team, please. So the presentation in which I'll cover the introduction, the motivation for the carrying out the study, the objectives, problem statement, the numerical modeling. We did some parametric studies which I'd like to share with you, and then I'll share a brief conclusion of that. So basically tunneling in an urban area is a very big risk to the deformation. We have a very big risk of deformation of the existing structures, and this problem is not very new. Its problem is worldwide, and specifically in India we have seen many unfavorable incidences which have happened. Some of them are like in Kolkata, you all know that some incidents happened due to tunneling. There was also a collapsed building in Agra Metro recently, and so on. So what is the need for actually doing the motivation doing this analysis? That most of the studies which are available here rely on 2D analysis, and we miss many things while carrying out 2D analysis, like we miss the phase pressure. Obviously we have indirect ways to model it, but we don't model it directly. We also miss the pressure put by the jaws on the existing segments. We miss the grout pressure, which controls volume loss to a larger extent. So there are many things. So that's why we tried to use 3D to see how close we can be to the actual observed values. And for this we have taken the Meerut Delhi corridor project, and we have done the analysis on that. The objectives were that we should predict the TBM settlements and then compare it with the values which are obtained by empirical relations as well as the actual data observed. We have done the analysis comparison with respect to actual data observed, but we didn't got the permission from the concerned authorities as of now to publish it. So the file is under process. So this presentation will be restricted to the comparison to empirical relations. Although we have done the comparison with the actual data observed, and there were some things which I'd like to share, what were the observations during my presentation, but we were not able to publish it here in this paper. Then we also did some parametric studies to understand the effect of ground pressure and phase pressure on controlling the volume loss and the settlements which are observed on ground. So as I discussed, the data used, the project which we undertook was Delhi Metro project, and we did it according to the requirements of the authority, right? So basically this was a layered soil medium. So the soil medium comprised of different layers, and I marked the layer thickness to the scale and also the tunnel diameter and other things in this picture. So these are the soil properties which have been considered of different layers for the analysis. We have also modeled the lining as an elastic medium, and we have started our model from certain distance from the tunnel, because when we were starting it from the face, there were boundary effects which were coming into picture, and the results obtained were not very realistic. So we started it after installing 12 segments. Then we started our analysis. So this is the way we have done the numerical modeling in 3D of this project. So the results which we have got here is like this. We have obtained the longitudinal as well as transfer settlements, and we have actually considered the load of buildings also, because it is in 3D study, right? So wherever buildings were in approach, we have applied the vertical load of those buildings at the respective locations, knowing the foundation from the concerned department. And we see that our results were very well matching with the empirical relations which were available. However, when we did the comparison with the actual observed settlements, the actual observed settlements was on the lower side than our predicted value. That is what broadly. They were matching somewhere, but broadly they were on the lower sides. And there is a reason behind it, which we can understand. Because the persons who are actually installing it, the settlement markers, they are not taking it sufficient deep. They're installing it only on the top layer. So if you do so, then you will not actually get the settlements. You'll get something which is moving, but not the whole ground. So that, to the best of our analysis, this we found as an biggest reason for that. So we were actually obtaining a settlement which were underestimated than actual settlements which might have been happening there. And this we have cross-checked also by reinstalling at certain other locations very deep settlement markers going to around, with a road going to around 2 meters deep. And there the settlements value observed were on the higher side than those which we were using only 250 mm or something depth. We see the effect of ground pressure and as well as the phase pressure, and as expected the settlement values were going down once we improve the ground parameters with different ground pressures as well as with the phase pressures. So the conclusion here is that this is the 3D and finite element analysis, and because we are doing in 3D, we were able to model all parameters which could be a affecting parameter. Like we were able to model the phase pressure, we were able to model the ground pressure, we were able to measure the jack pressure, the jack thrust which TBM is putting for moving forward. We were able to model the actual loads of buildings which are coming at the respective locations, and we were able to study the variation because of all these factors. I mean, this is only a part of our whole study. The remaining study we are publishing in World Tunneling Conference, which will contain all, provided we get the permission from the concerned authority. Thank you everyone, and I will be happy to answer your questions, whatever, if I can.
Any questions?
Sir.
Under impression that all these surface markers are put on surface only.
Yeah.
But after your talk, I have come to understand that they should be put little bit deeper.
Yes, sir. Definitely, sir.
And in most of the metro projects, I
Sir.
think you are one of the parties who are responsible for putting these markers.
Sir, I 100% agree with you. I mean, our company is one of the party, but I am from a consultancy division, so I'm not very sure of that.
Okay, so
Yeah.
but
But yes, you are right. Even our people do the same thing.
you can discuss
I
with
can
your
appreciate- I know they do the same thing.
And is there
Absolutely.
any code for this? Is there any standard for this? That how much deep these markers should be placed?
Sir, there is an IS code for it, but I believe that even that IS code needs revision, because if you see the international practices and that IS code, it was published very before it's actually under revision. I am a part of that technical committee who discusses that, and this point is well appreciated by all the
So
members.
sooner is better.
That I cannot say, sir, because it's a long process to revise an IS code, but
I
that
am-
is the biggest challenge, sir.
I am being professional in this field.
Sure.
I was not aware that
No,
all
it-
these surface markers we are putting on surface is not correct.
It's not
and,
actually.
and
it's not, sir.
logically it makes sense
It
because
is, sir.
there's some
Yeah.
upper soil
Yeah.
which is not elastic to that extent.
And then,
so
sir,
it
yeah.
will not settle. Ultimately, lower
Yeah.
layers may settle,
That's
but upper
right.
layer may not settle.
That's right.
And being in the, I think you are the leader in this. Your company is leader in this field.
Yeah.
So it is better that IS code is amended as early as possible. Otherwise, we will keep on doing these mistakes.
Sir, I can share the information that the committee has accepted this suggestion, but when it will come, I think it will easily take a year or something, sir, because the process is like that.
And another problem in a congested city like Chennai, Mumbai, even you don't get a space to put markers on surface.
Yeah.
So you will have to come up with certain solution that how do we put 2 meter deep under those hutment area where there's no space.
No,
So
but
that
it is only a road, sir, which goes down, right?
roads are not there.
No, I'm
Or-
saying only a steel road, ROD road.
For putting rod also, you
Yeah.
need some open surface.
No, that's
so
right.
Mumbai in hutment area, there's no open surface because along the tunnel alignment, you have to put 5 meter or 10 meter both sides.
Yeah, you're right.
There you won't get space. So
sir,
just do some research in that field and find out how can that be, that problem
Sir,
can be resolved.
Here, sir, just I'd like to share my experience because previously I was working as a GC in Lucknow and Chennai Metro also. So what I've seen is that you can stagger them. It's not required to put it in a line. Wherever you get a space, there is a general practice that people say, I have to put it line, then only I'll compare. No, doesn't matter.
I
Where you
agree.
get I think even if you get a point cloud on a map which shows you settlement, you can very well draw the drafts afterwards,
So
sir.
Lucknow condition is different,
Yeah,
but
yeah.
you
But that's a
might,
challenge,
you
I
might
agree
have
with you.
experienced in Mumbai also. Your company has worked in Mumbai also. Mumbai conditions are entirely different. You will not
quite
get
possible,
any
sir.
even gullies are not there.
Yeah, then it's a challenge.
100% covered area.
Mhm.
So that's a food for thought.
That
to
is
you.
a challenge, sir.
Yeah, right.
Thank you, sir.
Yeah.
Thank you. Thank you. No, you are right. Actually, it should surface settlement marker. I think actually, Kandharb, I will be going against you. But instead of putting a 0.25 settlement points deep settlement marker, again I'm going against you. It will be better to just mark a plus sign and measure it's by a level. You don't need anything actually if you're doing that. Just do the surveying and take the deformation by a leveling. No point in putting that. Matlab nahi. Settlement marker. Yes. Yeah. But again, then at least it will reflect the settlement of down layers, not the top one, no. And that layer is already a bituminous layer or is relatively hard layer, which is not deforming with the ground. So you need to understand before putting it. That's what I can say, sir. Yeah. Thank you. Any other questions, sir?
So next presentation title is ground subsidence of the circular tunnel under static and seismic load. Is the presenter available? No. So then the next presentation will be appraisal of the phase stability of in soft ground conventional tunneling.
I'm unable to access this. Oh, okay. Oh, okay, sorry. Ma'am, I have the PPT file as well, so I'll. Cursor.
You can open the PowerPoint.
I think it came. Good afternoon, everyone. I'm Animesh Sharma. I'm Assistant Manager Civil at National High Speed Rail Corporation. National High Speed Rail Corporation is constructing the first high speed rail in the country. I'm also a PhD candidate at IIT Bombay. So the topic of the today's presentation is appraisal of phase stability in conventional under-drain soft ground tunneling. As the title itself suggests, it's a validation study using a real case study, validation of the phase stability models and under-drain ground conditions. Undrained ground conditions, particularly in soft ground urban tunneling today, as it has been already discussed in the prior presentations, in urban context, it is very important that the stability and the ground deformation is of utmost importance. Tunnel stability is a very essential criteria, particularly in soft ground construction. Tunnel stability, the stability of the face as well as the deformation, they matter a lot because of their impact on the existing infrastructure. The earlier studies can be traced back to Taylor in 1937, whereby a phase stability model, phase stability charts were proposed by him, whereby vertical cuts, stability of vertical cuts were proposed as a function of the shear strength of the ground and the ground parameters and the geometrical parameters. As late as in 1967, 1969, Bromson, Bennermack, Peck, Horn et al. In 1960s, they proposed certain models for the phase stability. Particularly in undrained condition, the stability has been proposed as a stability number, as an index rather than objectively defining. So using the experimental study, centrifuge modeling, and the numerical some case studies, these were the formulations. These were presented by in 1960s by Peck et al., Bromson, Bennermack. Further, by 1980s, 1981, Davies et al., they had presented upper bound and lower bound solutions in context with different cover to diameter ratios. In changing cover to diameter ratios, they had presented upper bound and lower bound solutions, whereby the stability of the tunnel opening phase in undrained conditions were proposed. These studies were again validated using centrifuge modeling test by Kimura and Meyer in 1981. So in summary, if I may put it, this was the bottom table highlights the number of models they were undertaken and what are the key function parameters that are relevant in that context, what the formulation of the stability is a function of. Again, this FHWF, Federal Highway Authority, they had formulated this table whereby they had, in cohesive soils and sandy soils, they had provided a critical phase stability number. So in general, the consensus regarding this phase stability is that in case if the stability number is less than 3, the ground is considered to be stable, considering the given parameters. Whereas if it is between 3 to 6, it might not undergo the ultimate limit state failure, but it still might have some serviceability issues. Whereas if the phase stability n number is greater than 6, it is most likely that it is not considered to be safe. Over time, various studies, analytical, experimental studies have indicated that phase stability causing ground deformation, it is an essential function of tunnel geometrical as well as the geotechnical parameters. Now, ma'am, I'd like to, everyone, I'd like to present this, in context with the validation, I'd like to present this study in context with the Kolkata East-West Metro, UG1 project, which was the tunnel, 3.8 kilometer tunnel, twin tunnels that was being constructed right from the Howrah station up until the, I forgot the name. But these tunnels, as we can see that in geological context, and these, there were almost all 8 cross passages. The geology primarily comprised over here of soft clay, as it is highlighted in the upper section over here, that this was very soft clay. Its UCS value varied from somewhere around 25 to 50 kPa, which was underlain by a stiff silty clay. The UCS value was somewhere around 100 kPa, and there was an intermittent sandy clay over here. It was present. The main tunnel was constructed using tunnel boring machines, whereas the cross passages were constructed using NATM method, conventional tunneling. So here, as we can see that 4 of the cross passages, CP1, CP2, CP4, and CP5, they were essentially located in the total stress condition or the undrained condition, whereas other cross passages, they were in effective stress condition that comprised of sandy, silty clay. I have laid out the geotechnical parameters and material conditions of the parameters over here. It was first up till 0 to 3 meters, it was fill soil, then it was underlain by soft clay silt, very low shear strength, and even in drain conditions it had a lower effective strength. But the permeability for both the contexts were very less, the entire ground, since it was in total stress conditions. And even the Young's modulus values range from around 10, 15 MPa, and over here it was around 32. So phase stability assessment, as we have discussed earlier, that it is a function of the cover to diameter ratio and the undrained cohesion of the ground. So essentially for these cross passages, whatever undrained cohesion values, I mean, if you put in the parameters, so these are the critical failure lines, essentially where it is considered that this is the failure zone, if you can say. It is a critical line which basically denotes that beyond this, underneath this, just similar to the Mohr-Coulomb criteria that we have, underneath this, if we have the stability number, it can be considered as safe, whereas over that it is considered to be unsafe. And as we have previously discussed as well, underneath 3 to 6, it might have certain degree of serviceability criteria. So based on this analysis, it was seen that the ground parameters in CP1 and CP2 particularly, which were located in very soft clay, they had phase stability number which was greater than the required. Phase stability number, the stability was not met in this case. This study was again validated using the Taylor stability number. Taylor stability number again provided that the CP1 and CP2 were essentially having lower factor of safety given the conditions. Due to this, a ground improvement methodology was adopted through the tunnel locations itself. This section was entirely grouted using sodium silicate and cement grouting. And this is the plan section. This is the opening over here. At these locations, the grouting was undertaken. It was undertaken in the undrained condition in the clayey soil, which had a very low permeability. So it was essentially a replacement grouting, if we can call it, because the ports were provided on both the sides. And when the grouting was done, some of the soil was replaced from one side. And essentially, over time, when grouting was done, this entire section was strengthened. Now, when in context with the appraisal of the phase stability model, it is usually, since we have discussed it earlier, it is very difficult for identify a physical index or a phase stability factor in the ground conditions. So in order to assess, since the locations of the cross passages were located at I would say that they were not very approachable at a surface. There was a certain degree of either railway tracks were there, even there were buildings. So because of that, it was not possible to undertake a soil investigation over there. So this undrained cohesion, the essential parameter shear strength, was assessed using in situ pocket penetrometers. Pocket penetrometers were used for assessing the undrained cohesion of the post-grouted soil. The pre-grouted soil, we already had undertaken the soil investigation, and for the during the tunnel excavations, these were assessed using pocket penetrometers. Considering those values, considering the histogram or probabilistic analysis aspect of the values that we were certain, these values were further validated. The undrained pre-grouting and undrained cohesion from the soil investigation data, such as triaxial, UCS, SPT, these were considered, whereas for the post-grouting, pocket penetrometers were used. The data set histograms were plotted to cater in the uncertainty and the reliability aspects. And the critical phase stability models, I would. So these are the histogram plots of the yellow over here shows the pre-grouting considering the SPT, UCS values, the UCS values that were considered for CP1, CP2, CP5, and CP4. As it can be observed that there was a certain increment from the after the post-grouted soil. The average increment was somewhat in the tune of 30 to 40% in almost all the kind of soil. This is the table which basically highlights the pre and post-grouting at all cross-passage location. At cross-passage 1, earlier the mean was around 44, then it went up till 63. And even in CP2, earlier it was 50 kp around, further then it went up till 88. And here the mean averages have been plotted over here. So now when we put the same plots in this context again, in context with the failure stability criteria, we observe that the values now were within the stability range, and it was potentially possible to undertake the tunneling, the opening. And this was again validated using the Taylor stability number again. Here, so the dark black points, markers over here show that the post-grouting considerations, post-grouting Taylor stability number, these were observed, whereas the hollow markers show the pre-grouting conditions. So further, some certain, since the entire process also comprised of using some additional methods apart from grouting, such as using of 4 poles and other techniques as well. So it was really difficult to compare essentially the phase stability could be attributed to the ground improvement itself or not. So hence some numerical analysis was also undertaken. I won't be going into a lot of details. So the intent over here was, since we had standard charts which basically provided us for the C/D ratio, such as over here, but the C/D ratio basically existed up till 4 or 5 in this context, the C/D ratio of 4 and 5. So the numerical analysis basically intended to capture to the higher C/D ratio. Since these lines represent the critical failure line, or where the stability fails, so it was not possible to do in practical context, hence numerical modeling was done. And based on the several degree of iterations, apart from the charts which have been already presented, this was the chart that has been presented as a part of this study, which allows an extension of the chart right up till the C by D value of 7. So in conclusion, since the phase stability, including the ground deformations and the stability of the face, is an important criteria in the soft ground conditions, undrained conditions, particularly in urban context, ground improvement using chemical grouting was undertaken, which showed an increment in the tune of 30 to 40%. The enhanced parameters have been assessed. And so basically the ground improvement, the impact of ground improvement can be seen, can be correlated or validated to the phase stability model itself. And the phase stability charts have now been extended, have been proposed to be extended for their application for design and construction at deeper depths. So thank you.
Thank you very much. Any questions, please?
Yeah, at the same depth. Pre-grouting and post-grouting. Pre-grouting, they were undertaken using several, a cluster of data has been considered using N values, UCS values at the same depth where the tunnel openings were there, and whereas the tunnel excavation, the other post-grouting, they were taken at the face itself, so they did represent the values at the same depth.
But after post-grouting, you are doing with the pocket penetrometer, but before that you have tested using SPTN or
SPT, N value,
right, no?
UCS.
How?
Earlier, the entire, as we can see, that the geological context is similar. Over here, it is very homogeneous in context. So we have test results at different locations, and it is more or less homogeneous. There's soft clay which is located at different locations, and there's stiff clay which is located at the lower depths. So the standard values, they were taken at different locations. They were considered for this. Not exactly at the same location, but since there was a homogeneity regarding the soil strata along the length, so hence they were considered for correlating the values.
Understood. My question is, you are using different tests.
Yes.
For validating, no?
Yes.
Strength.
Yes.
So because inherently that itself will have some differences.
I understand, but there has been some study, which I think in the paper that I had cited, that there was a study whereby they had correlated. The study was particularly pertaining to the UCS values that was obtained using different tests, and the UCS values was obtained using pocket penetrometer. So over there, they had produced a very good R-square value of somewhere over 0.9 or something. So that basically validated that the use of pocket penetrometers justified the comparison over here in this context.
So, was there a design need of doing combination of both forepoling as well as soil improvement, or it was a safer approach adopted by the
As
organization?
a word of abundant precaution, because we were constructing
so it was
underneath
a safer
the safer
proposal.
precautions.
Otherwise, this soil improvement was enough.
Yes, through the validation, that is one of the points that I'm trying to make, that ideally it was safe. Particularly, I think in CP1 location, that might have been a relevant thing, but beyond that, I think that might have been sufficed.
Just one quick query.
Yes, sir.
Your CP1 and 2, you can see that your depth starts from 5 meter, whereas the ground improvement you started from 10 meter.
No, sir. So this is, it has been shown in meter MSL. So if you can see that the ground level is at 5 meters. The ground level is at 5 meters, and the top of the tunnel is at -5 meters. So overall, it becomes down to 10 meters. I have not put it as a meter below ground level. I have put it in RL, so that's why it was.
Okay. Thank you very much for your nice presentation.
Thank you, sir.
So the next presentation title is Design and Construction of Low.
Also mine will be. This one.
Good afternoon, sir and ma'am. My name is Krishan Singh. I'm Deputy Chief Project Manager, currently looking after the works of tunneling works of high-speed rail. This is just an overview of the project, how the project is being constructed. This is a 508 kilometer of project which is being constructed in between Maharashtra and Gujarat. The 4th station will be in Maharashtra and the 8th station will be in Gujarat. There are the viaduct comprises of almost 91%. 1.93% will be bridges. 5.16 will be tunneling. In this, the longest tunnel is the 21-kilometer tunnel, which is being constructed from BKC in Maharashtra to Shilphata in Maharashtra. Then the earth retaining structures and banks will be 3.9. The cut structures will be 1.3, and cut and cover structures will be 1.55. Stations, there are 12 stations, as I have already told. The travel time will be around 2 hours with the limited stops and 2.58 hours with all the stops. Right now, the tunnel which is being constructed in Maharashtra, that is a 21-kilometer tunnel. This is a layout plan, and you can see from here to here, it's a 21-kilometer tunnel from here to here, from this shaft 1 to this shaft 3. This section will be constructed through TBM, and from this shaft 3 to this Shilphata, this section has already been constructed, and this section has been constructed through NATM method. The TBM tunnel has a dia of approximately 13.1, and the NATM tunnel have a cross-sectional area of 120 meter, which has a width of 13.6 meter and the height of 10.6 meter. This is just again an overview from where how the work will be carried out. From here, this is the just a minute. From Chenish 4, this is the Thane Creek region from here to here, and we will be passing through this Thane Creek region through TBMs only. These are the shafts which has been planned in this region. From here, there is one 56-meter shaft, and here this is another 39-meter shaft through which the TBMs will be launched. This is a edit which has been constructed to facilitate this construction of this main tunnel. This is the plan of the case study which has already been carried for the tunnel, which has already been constructed. This is a cut and cover 65-meter cut and cover zone, and this is a two-way road which has been crossing, and these are the water pipelines. There are 3 numbers of water pipeline which is being crossing and from these we are crossing under these pipelines. There is one gas pipeline of 610 mm also, which is just above our tunnel. This is the geological details which has been showing that this is our cut and cover tunnel. From here, we have to start our tunnel, and these are the pipelines. And the geology is also very poor, as well as the cut, as well as there is a very low cover zone in this 120 meter of the tunnel. Then the stability part, the stability has been carried out. Different stability has been carried out. And along with that, the support measures were provided. The numerical part will be covered by Mr. Animesh.
I'd just like to go to the backside again. Am I audible, sir? So, sir, as we can see over here, this is the crown section of the tunnel, whereas this is the end, the invert part of the tunnel. So as it can be seen over here, the top portion was basically a fill ground, this entire section where the crown was coming, which was followed by a highly weathered rock, which was again followed by, so by the section of invert, this was basically we had a moderately weathered rock, or we could call a more competent rock. This section, it started with a cover of barely, I think, 0.51 meters in this section, whereas up till over here, the cover was somewhere around in the tune of barely 5 meters. So for a 12-meter dia, 12.1 meter, 12.6 meter dia with a cover of this much, along with having some operational utilities which had operational pipelines, which were supplying water pipelines, and an operational road. This was a challenging thing. I think the underneath photograph shows it allows you to better appreciate the context. This was the crown over here, and this was the pipeline which was existing, and this was the tunnel. And this is the cut and cover section, and this in the post portion that covers the viaduct. So as we have seen that the entire section comprised of basically a top clay soil. So for phase stability assessment, as if we get back to the phase stability aspects of that, phase stability again was an important criteria in this. So for phase stability, the study by Ananastu and Perazali was considered for the study. The silo, which was the silo study, which is existing since 1960, as provided by Horn. So the stability analysis was undertaken considering the different wedge angles. As we can see, we have a wedge model over here, and the wedge angle may vary depending upon the ground conditions. So for different wedge angles, the stability was considered. So stability, as it can be observed over here, somewhere around 500 kp of support was required if the wedge angle was somewhere between 30 to 40 degrees. Hence, basically, the phase stability required some form of support. The unsupported length was also assessed for the excavation of unsupported length as 0.5 meter, which also was less than the required. Hence, it was clear that some sort of phase stability measures were required over here. Settlement was also assessed as it was previously discussed in previous presentations. The PEC, the formula which was presented by PEC. So based on the existing literatures by Vitale et al. In 2021, considering the same diameter and similar geological conditions, the volume loss was assessed somewhere in the tune of 1.5 to 2% as per the reported case study. So considering the same parameters, it was assessed that the settlement might be in the tune of 180 to 120 mm, which was much more higher as per the requirements of the existing utilities over there. So in that context, multiple methods were assessed, grouting and providing a steel support system. Multiple methods were proposed, but eventually an umbrella arch method, which was considered. Now, umbrella arch method primarily comprises of these 6-7 aspects, going from application of 4 poles, application of shotcrete, ceiling shotcrete, face bolting at the face, which is shown over here at number 3. Then the provision of steel ribs, then provision of ceiling shotcrete again, and rock bolts as required. So this schematic is just for reference, taken from Hook and Marino's 2004. This was the support that was eventually used for the application. As it can be seen over here, this had a pipe roof of 76 mm. This was assessed using the formulations which have been presented over here. Though the spacing of was somewhere around 300 mm was assessed, but again, considering the word of abundant precaution, as per the calculation, it was coming around 700 mm, but again, as a word of abundant precaution, somewhere around 300 mm for serviceability criteria, 300 mm was considered. Pipe roofs of 76 mm dia, 6.3 mm thickness, 12 meter lap with 4 meter over thickness, I think, along with steel ribs. This is the cross-section view, which shows over here, which shows the ground level. This is where the portal, this was the portal location. Beyond this over here, from where this is where the tunnel section starts. The steel ribs were provided at spacing of 0.5 meter. This was again the formulation which was provided by Ananastu and Perazali, and also by Zhang et al. The charts that they have presented. So the bolt density for phase stability, the green sections which have been highlighted, the phase stability was phase bolts were provided. GFRP phase bolts of 32 mm diameter, they were also provided. This is the ground reaction curve which was plotted. So the reaction curve which has been made is considering only the steel ribs, not the other support measures which were considered. Steel ribs at 0.5 meter, and this was the ground reaction. So it can be seen that this is just an elastic curve that has been plotted, whereas somewhat elastoplastic curve is usually observed. So this was because in order to assess the phase stability, in order to assess this, the ground was considered as soil, not as rock. So beyond this, the plastic zone that showed basically an entire collapse or failure that was assessed. So in an overview, the phase stability aspect without support pressure required a phase stability the support pressure of 5600 kPa or somewhere around 4400 kilonewton using the rock bolts. Unsupported length factor of safety was 0.58. Settlement was over 100 and wedge failure, which was as per site conditions. This was the pre-support measure that was applied. Phase bolting was applied for phase stability. Umbrella pipe proof and steel ribs ISHB 150 sections were at 0.5 meter spacing were considered to cater to these two aspects, and the wedge failure rock bolting was considered as per the steel ribs. And the end product of that, the wedge support pressure slightly higher than the required pressure was assessed considering the provided bolts. So after a safety factor was found beyond 1.5, and the settlement in this criteria again was I'll discuss that on a later stage, how the approximately around 10 was assessed. So this is the schematic in the geological context, where it shows the couple of existing utilities. This altogether 3 utilities along with the existing road and a gas pipeline, and at a very low overburden of barely 5 meters. And this was the support system along with the face bolting that was considered in this section. This was the cut and cover section right up till over here. Beyond this, it was the NATM tunnel, and right over here it was the viaduct section. Numerical analysis was also undertaken. This is just a schematic of the numerical model, and this shows the parameters, the material elements, plate elements which was considered, and the soil parameters which were considered for the analysis. This is just a schematic of the umbrella arch model that was undertaken using plate elements, as it can be seen over here. Heading and benching, 2 aspects were considered. So this basically shows the forepoling, whereas the other aspects shown in the center, they basically represent the phase bolts. The results were pretty eminent over here. The results without phase stability, it showed a settlement in the tune of 131 whereas with the provision of steel support, this support system, the displacement values were in the tune of around 10 to 15 The safety factors, this plot shows the horizontal displacement at the face, which was again with the umbrella arch method, it had come down to a very minimal number, and whereas the phase stability using the 5C reduction technique, which was assessed using numerical analysis, was in the tune of 1.4 in this context without phase stability, whereas it went up till around 3.5 with phase stability context. And now the construction part, I'd request Krishnan Singh sir.
So these are the pictorial view just for how the construction has been carried out. Yeah, please. So this is the tunnel. These are the how the pipe roof has been carried out. This is the face bolts that has been constructed into it. These are the ceiling shotcrete. After that, the ribs has been installed. Then the rock bolts has been installed, and the various instrument were also installed to cater and to record the settlement which has been carried out. These are the instrumentation values, and till date also the instrumentation are also installed, and there is almost negligible settlement in the tunnel. So this case study shows when the with precise design and the values and without disturbing any utility, the higher tunnels can be constructed. Thank you. Any question?
Technicalities, but would like to know what is the nature of your contract? It's a design and build contract, or it is measurable contract?
No, it's a design build contract. Basically, the design has to be provided by employer only. So the work has to be executed by contractor, but the design is to be done by the employer only.
So when four polling spacing is reduced,
yeah,
employer is bearing the cost?
Yes, employer is bearing the cost.
Okay.
What is the water table? You have any problem with water table?
At that, the water table was high, but we did not find any water in our tunnel. There was slight seepage, and that has been catered with the grouting works.
Just I want to know, any limiting settlement you have considered, or by designer it is given? What is my limiting criteria? How much settlement is allowed?
No, we have considered the settlement of hardly 2 to 3 mm in this design. In our design, there was no settlement given, but as we have to execute the work and we have to open the face, and when you open the face, there will be a slight settlement in your soil. So we have in the design we have considered 2 to 3 mm of settlement, but however, after constructing and during the construction, we didn't find any settlement in the. No, sir, because the section is lower and the geology as well as the overburden is very less there. So we cannot execute the work with the TBM section. This must be part of ramp. Yes, it's a part of ramp. Yes, exactly, sir. Yes. For the face support, for when you open the face to so that the face does not collapse, you require that much amount of pressure to so that yes, yes. No, because yes, but there is a two-way road on which the traffic is continuously moving as well as there is utility. Yeah.
So
Okay.
here,
Yeah.
the pressure was somewhere around 120 kPa itself, but over there in that context, we were considering the weight of the entire wedge.
No, even if it is like 5 meter, so just check that.
So I think the support pressure, basically what we assessed was in the tune of 120 kPa. No, in this context it was 120 kPa, but for the support pressure, what we had assessed, I'll still check.
Yeah.
sir.
Okay.
I'll still check.
Thank you.
Okay, thank you very much. So it was informed that three presenters not available. Still, I'm just telling
The last presentation.
Yeah, last presentation. Yes, but still, I mean, let me see that whether the presenter is available. The title is Effect of Tunneling on the Ground Surface Movement. Presenter available? No. Next presentation, Impact of Nearby Excavation on Stability of Existing Urban Tunnel. Is anyone available? No. Next is the performance of tunnel boring machine in Holistic Deccan Trap Rock, a case study. Okay, so then we can move to the last presentation, that is stability assessment of the water curtain tunnels in a very poor rock mass.
So Chairman, I have more time to speak.
I think we have to close. Less time actually.
Less time, only 7 minutes are left.
So I need a screen पर. Okay. Okay. Good afternoon, everyone. So, this being the last presentation. So, from the soil tunneling, let's move to a rock tunneling part. So, I am Dr. Altaf Usmani, representing Engineers India Limited, and as part of the tunneling, most of you are involved in the infrastructure, but I am a different group. We are from the energy group. So, we are working for tunneling for a different part of the study. I will just explain you briefly this project because this is a very large project and it needs separate time to start. But because the work is connected to this, so this is one of the biggest ever project constructed in India for storage of LPG gas. And this project is a rock mechanics thesis. It involves everything. All tunnel sizes, all rock classes, starting from soil. Just to give you an overview of the project, this is a storage project where we start from the portal ramp, which is the soil part. We move through the access tunnels with a slope tunnels. I will explain the scope. Then there are the main storage galleries, which we call as the LPG storage caverns. So this, from this level, we are almost going 200-meter deep inside the rock. And when I say that this completes all the rock mechanics, we start from an open portal ramp soil. We start from small tunnels, 5 meter, 6 meter, 7 meter, 8 meter, and then we go So this is the largest underground cross section built in India. The first one that you see, it's 1 kilometer long, 31 meter high and 20 meter wide, around 600 meters square of cross section. This is already constructed for crude oil, and that's recently constructed LPG storage, which we will be discussing, 80 meter wide and 21 meter high. This is also around 300 meter long. So these two are the main storage area where we store our energy products. Now coming back to this, so this one, what I was showing to you was this part. Now as part of this project, there are lot of tunnels, lot of issues with the tunnels. In this one, what I will be discussing today, this is the problematic area, the red one. So this problematic area represents, it's a water contained tunnel which carries all the water, and the whole lifeline of this water. I will explain you how, so this is the principle how we store any product. This is called the principle of hydraulic confinement, where you store the product inside a cavity, a natural rock with no supports almost, and you have the water contained tunnel at the top. You get the required hydraulic pressure, which is more than outside the inside pressure, and this way, all throughout the life of the project, which is around 50 years, we preserve any product inside the cavity. So this principle is working fine. In India itself, we are working more than 30 years in this project, and worldwide it's more than 50 years. So this way, that's why we require this water contained tunnel, which we store the water, which is connected to the boreholes, and that gives the required pressure to keep the product intact inside the rock cavities. Coming back to that water contained tunnel, which is we will be considering here the critical part. Now, one most important part about this project is that we follow an observational method of engineering in these projects. When I say observational method, we start with every designer, some design is given to us. Basically, we are the complete detailed design consultant, EIL, and the basic design consultant. So we start with some design, but because of the challenging conditions, there are a lot of changes in the design. And the designer has to adopt as per the existing site conditions, the changes required to be carried out. And today I will be presenting one of the challenge that we observed. So we moved away from the basic design to the actual face mapping of the tunnel. So this design is collaborated with the face mapping tunnel design. So this is the small part, the smallest tunnel in this project, which is 5 meter by 5 meter. And as I told you, this is the part of the after execution. This is completely filled with water, and through which the boreholes are supplied for the required pressure, just schematic. Now coming to the problem. So when we were constructing this tunnel, after around 500 meter of length, we encountered 2 dikes in one of the section. So these dikes are basically a kind of a weak layer hydrothermal alteration, which was part of the main rock. And when we encountered these two, they were suddenly, when we were going through this passage, there was first dike which is going along the wall section, and then there was another dike which is cutting the crown section. So the interesting part was for the designer was that 2 dikes were intersecting, and this was a surprise to us because that was not part of the design that we did based on the initial investigations. Now during the construction part, these kind of surprises are there whenever you are doing an underground project, and you have to deal with these kind of things while adopting the design challenges. Now this is the face mapping of that same tunnel. Whatever the geologists have determined based on the Q system, whatever the rock classes were there, the volume, the RQDU, the numbers. So they came up that it's around 0.25, and you have to adopt a system as per the Q. But sometimes what you see as workable in the paper do not work in the field. So how we have to take into account that this support system works in this condition. Sorry. So we have to see how this support system, which was based on the actual face mapping and actual area, how this system can be worked in the field. The biggest problem while we were trying to execute this system was the site challenges. I will come back to this part later on because let's see the picture for better representation. So there are three ones. This is just during some part the rock support works were going on. This is at the part and this is the final one. So you can see as in addition to whatever the rock quality was there were lot of small overbreaks, seepages and small blast induced damages that were created all around this tunnel. So whatever we do as part of the RRS, which is a standard support in the Q system, but for this support to apply, you need a layer, you need a clear face where you can put these bars, where you can install the rock bolts. So a clear-cut representation, how to put this in that kind of condition, that was the biggest challenge for us. Now coming back, how we moved or approached this problem. Yeah. So there was one part as part of the design we studied as part of the analysis. We tried to simulate what was the actual conditions, how the dikes were crossing based on the orientations, different material thickness, material layer. We have a fair, poor, very poor. So everything was done, what was required as part of design. A numerical analysis was done, mapping was done, physical verification was done. These were the parameters that were used for the analysis purpose. The interesting part was that when we did the analysis with and without the support, how much we are able to control after the RRS. So that was pretty okay when after putting the support. These were basically the with and without support, what are the yielding zones we were getting. Now the major problem came and how we try to move out, that because the excavated surface was quite uneven with many overbreaks, so RRR bar cannot be directly installed. So what we did first, all the surface that was there, that was stabilized with a shotcrete layer to making a even surface. But as I told you, there were a lot of overbreaks issues, lot of small pockets. So as an improvisation of the support, what we did, rock surface was stabilized with first the shotcrete, then small bowls were made. That bowls were consisting of a wire mesh and shotcrete. They were specially created at the site and filled at the locations, and they were anchored to the surface inside so that they don't fall. I will show you in the picture also. As a step 3, the RRRs were only installed once we get a clear surface to put these bars, because then only it can be made effective. You can directly do it. And as a step 4, all whatever was put, improvised, was covered with the shotcrete to feel as it's completely RRS support. So during the installation part, so this was the initial things. So you can see a lot of pockets were there. When the contractor was trying to do initially, he was filling it completely because he was given a design and he was trying to execute. But the surface was not available to execute. So we revised the design. We first try to fill the faces. What are the pockets are there? We first make the face even so that the rock bolts or the RRS bars can be put. They were completely anchored or pulled to this one. Lot of rock bolts were drilled in this area to make this intact. And then finally, the shotcrete part was covered, and this was the final picture of the RRS system installed in this support. So whatever the challenges we got, we were able to improvise the rock support condition based on the existing site condition. Thank you. So that was the part. Both. Earlier, Government of India started with the security. That's why we work on strategic. Now it's commercial because we are building. No, sorry. it's like for LPG storage what we did, there is no land requirement. We built these projects within the available area. I have not included that presentation, but all these cabins are existing or below the existing facilities. So land cost is zero, maintenance cost is zero. No, that also depends on the amount of storage. We did this for 1 lakh metric ton. When you compare it with the above ground, which is small tanks of 1000 ton, 2000 ton. So we have worked out the cost. In case of LPG and underground, lot of profits have been made by the owners over the years. They fill it when the cost is low, they sell it when the cost is high. So it's now a business game nowadays. Refinery, all the refinery part, everything is at the top, and we are doing it 200-meter deep.
Who are the clients? ONGC?
In one case it was ISPRL, in HPCL, ONGC, different owners are there.
And generally, who are the contractors?
Contractors are SCC is there, SKEC Korea is there, L&T is there, Megha is there, lot of contractors. But we never give them design part, they are only constructing part.
I have a small question here. As you rightly said that these all are unlined tunnels. So that means we are relying completely on rock bolts and RSS for our support.
No, this RS was only for particular for 5 6.
For this area, I'm talking of this
only
area.
for relying for short.
Sure. My question is for this only. Remaining I can very well understand. So these do have a life of 20 years, 25 years. After that, don't you think it will fall?
No. See,
Why?
once we do the analysis,
Yeah.
we take into account, see, the life of the project is determined the life of the material that you are using.
That's
Okay?
right.
So there is, in this case, it's all short treated. There is
Sure.
no contact with any, whatever we are storing, either crude or LPG. There is no corrosive activity.
No, shortcut will live. I'm not have a question on shortcut, but the bolts will not live more than
The
25 years.
Bolts also, nothing steel part is visible. Everything is covered with short treat.
So he is confident that though it is SN bolt, but it is not exposed to oxygen.
Yes.
So it will not get corroded. That kind of confidence do they have?
And the,
But our
so you
solution
can
would be
use
to go
CRS.
for GFRP bolt
Yeah,
rather than
that was
SN bolt.
a recommendation
Sure.
going on the GFRP. A lot of
Yeah.
people are, but the best thing is that once these cabins are built, these are inertized. There is no oxygen inside
That's why.
because these are fireproof cabins.
That I know of you
Yeah.
from other caverns, but specifically this is a water tunnel where you will have water is required to go out, right? That's why I asked. The question is specific to this.
Whatever the bolts,
yeah.
steel bolts, we have a recommendation
Yeah.
for GFRP.
Yeah,
Till
I
now,
think-
this has been successfully used and every part is covered. None of the part is exposed to any of the chemical or the water.
So, thank you, Dr. Usman.
Thank you very much, Dr. Usmani, for the nice presentation. So, as the no presenter is available, so now I request Professor Maji to hand over the memento to our presenter of the thematic lecture, Professor Preeti Maheshwari.
This session, beautiful session, which like one theme lecture. Hello. One theme lecture, nice theme lecture by Professor Preeti Maheshwari, followed by the contributing lectures. There were 11 papers. Out of that, only 6 were presented. And you might have marked that all were in tunneling, and all very applied papers and very informative. I think it's wonderfully presented. So we thank the theme speaker, Professor Preeti Maheshwari, and followed by all the speakers and the contributing papers, the speakers. So thank you so much for coming and presenting. So with this, I conclude this session and hand over to the
Thank you, chairs, co-chairs, for timely completion of the session. And this was something of interest because we covered a lot of analytical approach to the problems. We had covered much of the synthesis of analysis and the execution in some way. So thank you very much to the chairs and co-chairs. It will be really my privileged duty to invite Professor Madhvi Lata to hand over a memento to the chair of the session, Professor Maji.